Okay, so we discuss what term two body problem. Two body problem has lot of yes green नहीं चलेगा अभी तो एक्सेल ने ग्रीन ने लिखा that you were able to write okay I'll write here
हाँ सर आगे बोला
so the thing is two body problem as such quote unquote has lot of meaning but normally in IITs we have one popular meaning for two body. So you see husband is professor at one IIT, wife is professor at a different IIT and there is a two body problem. But unlike this is involves particles and so if you have two particles 1 and 2 okay what do you expect? You will expect both of them to be under the influence of each other's attraction. So, you will have some force F in this direction and this will be experiencing minus F. Okay. And apart from that, you can have an external force in some arbitrary direction P which is acting on the particle 2. Now if you go back to the start of the central force motion right at the beginning, we had some assumptions. Do you remember? One important assumption was that gravitation is the only force. ठीक है? But यहाँ पे क्या हो रहा है? That assumption is being relaxed. So apart from gravitation, there is an external force P which is acting on particle 2. And another important assumption was the ratio of masses. If you see m by m naught was very, very small. M naught was supposed to be massive. So we relax these assumptions. So this is relaxed. Relaxed means this can be, the masses can be anything. Okay, need not be very small as compared to one another. And the second point, gravitation is not the only force. You have also an external force P. Right? So, if you want to formulate this problem and understand the dynamics of these particles, now it is a system of two particles here. So many pens, which one is the best performing one? So, if you want to formulate, understand the dynamics of these two particles, first of all, this is not going to be a very straightforward problem, and that is very good for you. Why? Because it is not a straightforward problem. It will require computers. Therefore, I cannot give this problem in the exam. This, then why am I teaching it? For the sake of completeness, and you will be able to appreciate why we went for these assumptions. Okay. And one more thing, you will also learn in classroom whatever is taught, that is always bounded by some assumptions, making things very idealistic. Now, classroom or research में क्या फर्क है? You take one of the assumption if you want to do research and you relax it. It slowly starts progressing to a research problem. For instance, Euler-Bernoulli beams, classroom problem. Effect of shear deformation is negligible. Relax that assumption, take a kick beam, Timoshenko beam. Moves closer to the realistic situations. So you tweak the textbook material or the classroom problems and you can formulate your own research problems, which is a very important part of learning. So, moving forward, what will be the free body diagram of M naught? This force F is going to act. That's the only force which is going to act, and that will be equal to mass times acceleration is equal to the force F. And how will you write this force F? You can write G M naught M divided by, now this R, it is actually R square, right? And the direction is in the direction, this is the direction of vector R. So how do you generate a unit vector in the direction of R? You write R vector divided by R magnitude, which reads as G M naught M by mod of R cube and R vector. So, if you expand equation 1, you will have G M naught M here. I would like to do a small manipulation. ये जो R है, this particular R, you can express it as R2 minus R1. And I hope that is convincing. So, you end up with similarly, how will you write the equation of motion for the second particle? This is EOM for particle 1. And this is equation of motion for particle 2. So what will be the free body diagram of mass particle M? This this direction, which is actually minus f. So you have m r2 double dot, which is mass into acceleration, and the net force. So you can write minus g m naught by m Is this convincing? So your R2 let me name the equations. This is still 1. Just arrange form. There is a 2. There will be a you can further rearrange this 1 as R1 double dot GM. M not cancels GM. That's correct. Okay. So here one thing which is done, I will write this equation here itself. R1 GM the idea is that I want to do away with R1 and R2 and I want to study the line, that vector which separates or joins M1 and M2. What is that vector which joins M1 and M2 or M0 and M? R. So by any means can I, using these two equations, can I reframe a single equation which is just based on this vector R? Okay, so R2 R1 double dot. So what is that equal to? See, this part is same. R2 minus R1 I can rewrite as R. So I can write G R vector, and if you do the math here you get minus M naught plus M so what it comes out to be is so this is the equation of the perturbed two-body problem. questions here? So you are able to write this vector r which separates these two mass particles by this equation. This is the most general form of this perturbed two-body problem. Now imagine that if you are having a motion of the moon, let's say orbiting the earth, like I said, the masses are like mass of the moon by mass of the earth is 1 by 81, not so small after all. So here you can, P will be 0, okay, but here that m naught will be earth and here this will be moon. This will be 1 by 81, you know mass of the earth. So you can do these calculations. Okay, now what we had assumed was there is only gravitational force, so P was 0, and we had assumed that m by m naught is less than 1. Now if you have P equal to 0, it is known as restricted two-body problem. Now in this equation 4, what happens if you put P equal to 0? Restricted two-body problem. You will get or you can remove this and just write in your typical central force problems, what was happening was your m naught was much greater than m. So this, if you enforce the second assumption, you will get the conventional, the central force motion equations, whatever we had derived. Okay, that you will get. Because m naught will m will be negligible as compared to m naught. But if that is not the case, suppose your you are calculating the time period of, let's say, moon orbiting the earth. How much was that? It was proportional to 2 pi, how much was that, or 4 pi square? What was it? 4 pi square. Yes. 4 pi square by g. Let me, to confirm with this, let me erase this m and make it m naught. Now if there is a correction, then what will be, how will this be modified? As per this equation, this will become m naught plus m. That's the only change it will be. So this is what you have calculated, and the correction, the corrected time period. The corrected time period, or the most accurate, will be 4 pi square t square But remember, your accuracy with what is calculated and what is actual, the ideal one, they agree well when m naught is much greater than m. बहुत लंबा वैल्यू पे, बहुत बड़ा वैल्यू पे, m naught पे, if you give a small increment doesn't matter. Okay. But if these are comparable, then this matters. Okay. So you can appreciate what happens if you relax the second assumption. Okay. So this is all about central force motion theory. Okay. Now you will later on you will find that if you do simulations using, if you even relax this assumption and have comparable masses, you will find that there can be very what should I say, interesting motions, like you will find both orbiting around a common center or something. Okay. When you don't have P, you need not have P, but only if this is very comparable. But the way we have written the equations, we are only interested in this part of that. But if you want to look at the absolute trajectories, then you should solve individually 1 and 2 numerically. This you need to solve numerically. Okay. So how do you solve differential equations numerically? Have you heard of RK4? Yes. Fourth order Runge-Kutta. That is one. You can also have Adam-Bashforth. I mean, there are several numerical techniques, and if you use MATLAB solvers, that can also help you. ODE45. So this is all about central force motion. यहाँ से ये खत्म हो गया. Now you will solve some problems and you will try to understand why we have learned these things. So, you have copied this. Attendance is thin today. Billy the effect. All of you were there in the program or someone? Sorry. You appear to be a musician. Hairstyle says so. Guitar. Okay, please note down a problem. A satellite in a circular orbit. A satellite is in a circular orbit. Of radius twice r. So a satellite is in a circular orbit of radius twice r. R is the radius of the Earth. Okay. So, and there is another satellite, not another satellite, this satellite here, which is orbiting the Earth, needs to go to this point B. What is this point B? So this point is the orbit so it needs to move to a location B, which is supposed to be the furthest distance from this particular center of the Earth. So what is the minimum boost? What is the minimum boost? What is the minimum boost? What do we mean by boost? Delta V. Necessary to reach point B. Necessary to reach this point B is at a radius of 3r. So this is one part of the question, and there is a second part of the question. At what point this boost must be provided? At what point in the original circular orbit? At what point in the original circular orbit should this increment be provided? So the satellite, let's say, existing, it is orbiting the circular orbit. The pink one is the circular orbit, and the yellow one is in the intended orbit, which is supposed to reach B. So it may happen that your satellite is right now in a circular path, and maybe you decide that there may be a lot of debris in the path ahead, and we should change the track of the satellite. Okay. And you know, all these satellites have retro rockets fitted inside. So from the space station you can actually fire when you need. So when you fire, you provide additional thrust, which is the source of this delta V. And this delta V will finally, what it will do, first it was orbiting in a circular orbit, now receiving this thrust, it will go to point B. And it will change the original orbit to a different one, which is shown by the yellow dotted. So have you understood the question? If you have understood, you can solve. There are two parts to this question. What is the minimum boost, and at what point in the circular orbit should this increment be provided? So what ideas come to your mind looking at this problem? You can refer to the formula. First you tell me the idea. ऑर्बिटल स्पीड ठीक है, ऑर्बिटल स्पीड हमें मालूम है, किसका मालूम है? सर्कुलर 2r से जो जा रहा है उसका ऑर्बिटल स्पीड हमें मालूम है। तो डेल v में दो पार्ट है, जो फाइनल v हो रहा है और जो इनिशियल v है, दैट इज डेल v। So initial V, like he said, is the orbital speed which the satellite is having when it is orbiting along the circular radius. इसके बाद energy methods. Okay. But especially energy methods, you have to be careful. When the del V is not there, it is orbiting in this circular path without any firing, तब तक energy is the same. Once you fire the rocket, हाँ initial boost के बाद फिर energy conserve हो. Okay, so what he is saying is that you take energy between which 2 points then? After firing. But there is also one part of the question that where will it be fired? See the second part. At what point in the circular arc will you fire? तो जिस पॉइंट से फायर करेंगे वो एक पॉइंट हो सकता है और फाइनली जो पॉइंट बी है, ये दो पॉइंट बी के बीच में यू वांट टू कंजर्व एनर्जी. ओके, बट देन the energy has two parts, half mv square and minus gm1 m2 by r square. r आपको पता है दोनों केसेस में, बट v कोई एक v तो आपको पता होना चाहिए. So what v you know is the circular speed. बट फायरिंग के बाद वो भी बदल जा रहा है उस पॉइंट पे, एंड दैट यू डू नॉट नो. यू अंडरस्टैंड? पॉइंट बी पे तो भी पॉइंट बी पे पॉइंट बी से भी निकाल सकते हैं. हाँ निकाल तो सकते ही हैं ऑफ कोर्स, प्रॉब्लम दिया हुआ है कैसे निकाल सकते हैं. प्रॉब्लम कैन बी सॉल्व्ड. Yes, वो elliptical path. Okay, that is another thing. So, elliptical path will help you to calculate velocity at v. But this is before you calculate the velocity at v, it is not really needed. आपको del v चाहिए. मतलब try to understand. Circular orbit में एक orbital speed है उसका. क्या है वो speed? Root gm by यहाँ पे 2r, रूट gm by 2r. ठीक है, ये स्पीड तो फायरिंग से पहले, then when you fire the rocket, then it has some speed. तो जब फायरिंग के बाद जो स्पीड है और फायरिंग के ठीक जो पहले स्पीड है, उन दोनों का डिफरेंस है डेल्टा v. Do you understand this? तो एक तो एनर्जी कंजर्व होगा ही नहीं. आपका एक स्पीड फायरिंग के पहले है, दूसरा स्पीड फायरिंग के बाद. Some work is done and there is a change in the kinetic energy, and therefore there is a delta. Do you understand? तो पॉइंट बी का स्पीड उतना रेलेवेंट नहीं है. पॉइंट बी हमें जाना है, राइट, with some non-zero speed. तो इसका मतलब जहां भी फायरिंग होगा, पहले तो वो समझना कहां फायरिंग होगा. जहां फायरिंग होगा, फायरिंग के ठीक बाद जो स्पीड है वही हमें निकालना है, क्योंकि फायरिंग के पहले वाला स्पीड वी ऑल नो, वो सर्कुलर ऑर्बिट का ऑर्बिटल स्पीड है. व्हाट इज द ऑर्बिटल स्पीड फॉर दिस सर्कुलर ऑर्बिट? But one of your observation is also correct. आपने बोला कि ये इलिप्स है. Obviously VC से थोड़ा ज्यादा है और एस्केप नहीं है. ठीक है, तो इसका मतलब वो इलिप्स ही होगा. ठीक है, so you have to which point you will fire, ये बहुत जरूरी है. First you understand this. किस पॉइंट से फायर करेंगे? यहाँ फायर करेंगे, कहाँ फायर करेंगे? यहाँ फायर करेंगे. Where is this location? B से सीधे you draw a line diametrically opposite this point. This is the firing point. where this velocity vector will be perpendicular to this, and this will become r minimum of the ellipse. ठीक है? R minimum of the ellipse. And what is that R minimum? 2r. Now you will be able to find velocity just after firing. तो कैसे करेंगे? Now all of the inputs we have received. Would you like to try? So at R minimum, the equation of the conic section is Gm by h square. Let me call this velocity after firing to be v. So h को कैसे लिख सकते हैं? r into v, कौन सा r होगा यहाँ पे? 2r. 2r into v whole square, right? Yes. What will be r max? H is constant by angular momentum conservation.
We will also change.
V will also change. PR में V will change, but I need not write that V which is there on 3R. I have to keep H constant. Okay. So what do you get? You can eliminate C. कितना हुआ? 4r square v square. How much is this? So how much is v? So what is the delta V? Calculate. Root Gm by R equal root 3 by 5 minus 0.5. एक 0.6 minus root 0.6 minus 0.5 कितना होता है? Are you clear that you had to fire from here? कहीं और से फायर करते तो ये जो 3R है उसके, क्योंकि ये बन जाता पेरिजी and that point would have been apogee. So if you fire from here, for instance, your V will shift over here. Can you fire from some other point, okay, on the circle such that it reaches B. I said कि मैंने यहाँ से फायर करना है तो ये B में चला जाएगा. Okay. But if I fire from some other point, I can fit a conic which passes through B. पास हो सकता है, तो पास तो होना ही है. See, in the question it was said that just you have to reach point B with minimum del B. The question is, कोई और ellipse जो B के पास करेगा, will that B be minimum? So that is something which you should think. मैंने यहाँ पे बोल दिया कि यहाँ से पास hit करना है, that is correct, and that B which you get is actually del B minimum. कोई और point से fire करते तो yes, you could have a ellipse, but that B will not be minimum. That is for you to think. हाँ, और कोई conic section भी हो सकता था, parabola हो सकता था, but then that will never come back. वो minimum तो होगा ही नहीं, because at 3R the speed will not be 0. It will be very high if you throw with a parabolic value. So this problem was not very difficult, requires little bit of thinking. Anything else? Let me ask you a conceptual question. So this is the Earth, and here you have a satellite. Okay. So there is this point A. Okay. So first what happens? You see the satellite above you. Okay. And then after certain point, the satellite completes one revolution, comes back to point A. Okay, but this time you will find that your line of sight with the satellite has changed. आपने ऐसे देखा चाहिए, satellite took one complete revolution, and that is a very long time. उसका one revolution बहुत long, आपको भूखे प्यासे उतना देर खड़ा रहना. I'm just visualizing. So you see the satellite passing above you. After certain point of time, when it completes one revolution, what will happen to you if you consider Earth's rotation? You will also rotate. Very good. So you will rotate and you will come to this point. So you will travel a certain distance actually. This is where you were when you saw it right above you. But when you come to B prime, you will find that your line of sight with the satellite has changed as it passes through the same location. So can you get this distance BB prime? You can get BB prime means your displacement. BB प्राइम माने आप यहाँ पे थे जब सैटेलाइट था, आफ्टर वन कंप्लीट रेवोल्यूशन यू आर नो लॉन्गर एट B, you are now at B prime. Why? Because Earth is rotating. टाइम पीरियड एक निकालेंगे, वेरी गुड।
टाइम पीरियड की वेलोसिटी कितना डिस्टेंस होगा?
कौन सा वेलोसिटी?
सर्कल जा रहा है।
Angular velocity. You have to compute, you have to know the angular velocity of the Earth. This omega must be known to you. You know it already because 2 pi takes, I mean, how much? 3600 into 24. That is the omega. Okay. And like he said, you should know, if you know the radius of this satellite, orbiting radius of the satellite, you will be in a position to calculate the time period. Circular motion में time period दिखाते हैं ना, if you know the V, what is the time period? Okay. So once you know the time period, you can just write T into omega. So omega is essentially d theta by dt. That when you multiply by the time period of the satellite, okay, you will get this angle delta theta. And the distance BB prime then will be r times delta theta, where r is the radius of, नहीं r को इसके लिए इसको छोटा r लिखते हैं. So you understand that tracking of a satellite can be a good kinematics problem, क्योंकि जो स्टेशन और ऑब्जर्वेटरी जो एक सैटेलाइट को ऑब्जर्व कर रहा है, that is always rotating. Satellite is also moving. Now to give those coordinates in the absolute frame and also in the relative frames, that will require little bit of thinking and programming at their end. Okay. So to some of you who are interested in these stuffs, you see there was long ago a author known as Kane, WWE wala Kane. Kane and Levison, they first started, actually this subject actually has come up with their book Dynamics by Kane and Levison, where you will find mostly that they deal with dynamics of rigid bodies on space stations. Okay, how, so you will deal with kinematics, which is, let's say, rotating around the Earth, is also on a particular rigid body with its joints always in motion. So those kinematics are very much involved, but if you know the correct Keynes method in dynamics, you will be able to program it and monitor these things. Okay, so we will stop here because the another problem is a very big problem and it will require one more class. So we will meet tomorrow.